Yes, my name is Yoshua Bengio, and I'm a professor here at the University of Montreal. I also lead an institute called the Montreal Institute for Learning Algorithms that is specializing in my area of science, which is machine learning, how computers learn from examples.
And what is the difference between, you say, machine learning?
Yes.
But there's also this new thing called deep learning.
Right.
What's the easiest way to
Yes. So deep learning is inside machine learning. It's one of the approaches to machine learning. Machine learning is very general. It's about learning from examples, and scientists over the last few decades have proposed many approaches for allowing computers to learn from examples. Deep learning is introducing a particular notion that the computer learns to represent information and to do so at multiple levels of abstraction. What I'm saying is a bit abstract, but to make it easier, I could say that deep learning is also heavily inspired by what we know of the brain, of how neurons compute. And it's a follow-up on decades of earlier work on what's called neural networks or artificial neural networks.
So, what is your background that you got into this?
I got interested in neural networks and machine learning right at the beginning of my graduate study. So when I was doing my master's, I was looking for a subject, and I started reading some of these papers on neural networks. And this was the early days of the so-called connectionist movement. And I got really, really excited, and I started reading more, and I told the professor who was going to supervise me that this is what I want to do, and that's what I did, and I continued doing it, and I'm still doing it.
And do you think with your research that you are on a route or on a main thinking line, which will get you somewhere?
So it's funny that you asked this question, because it depends. It's like, some days I feel very clearly that I know where I'm going, and I can see very far. I have the impression that I'm seeing far in the future, and I see also where I've been, and there's a very clear path. And sometimes maybe I get more discouraged, and I feel, where am I going? It's all exploration. I don't know what the future holds, of course. So I go between these two states, which you need. Right now I'm pretty positive about a particular direction. I've moved to some fundamental questions that I find really exciting, and that's kind of driving a lot of my thinking and looking forward.
Can you tell me, because I'm not a scientist, and most of our viewers not as well, but can you describe for me where you think your path leads to? Because sometimes you have a clear goal and you know where you're going.
Right.
Where are you going?
So my main quest is to understand the principles that underlie intelligence, and I believe that this happens through learning, that intelligent behavior arises in nature and in the computers that we're building through learning. The machine, the animal, the human becomes intelligent because it learns. And understanding the underlying principles is like understanding the laws of aerodynamics for building airplanes, right? So I and others in my field are trying to figure out what is the equivalent of the laws of aerodynamics, but for intelligence. So that's the quest, and we're taking inspiration from brains. We're taking inspiration from a lot of our experiments that we're doing with computers, trying to learn from data. We're taking inspiration from other disciplines, from physics, from psychology, neuroscience, and other fields, even electrical engineering, and of course statistics. I mean, it's a very multidisciplinary area.
So you must have a clue.
Yes, I do. So one of the, well, it may not be so easy to explain, but one of the big mysteries about how brains manage to do what they do is what scientists have called for many decades the question of credit assignment. That is, how do neurons in the middle of your brain, hidden somewhere, get to know how they should change, what they should be doing that would be useful for the whole collective that is the brain. And we don't know how brains do it. We now have algorithms that do a pretty good job at it. They have their limitations. But one of the things I'm trying to do is to better understand this credit assignment question. And it's crucial for deep learning, because deep learning is about having many levels of neurons talking to each other. So that's why we call them deep. There are many layers of neurons. And that's what gives them their power. But the challenge is how do we train them? How do they learn? And it gets harder the more layers you have. So in the 80s, people found how to train networks with a single hidden layer. So just not very deep. But they were already able to do interesting things. And about 10 years ago, we started discovering ways to train much deeper networks. And that's what led to this current revolution called deep learning.
And this revolution, I didn't read it in the papers, so it's not front page news, but for the science world, it's a breakthrough. Or?
Yes, so in the world of artificial intelligence, there has been a big shift brought by deep learning. So there's been some scientific advances, but then it turned into advances in applications. So very quickly, these techniques turned out to be very useful for improving how computers understand speech, for example. That's speech recognition. And then later, a much bigger, I would say, in terms of impact, effect happened when we discovered that these algorithms could be very good for object recognition from images. And now many other tasks in computer vision are being done using these kinds of networks. These deep networks are some specialized version of deep networks called convolutional networks that work really well for images. And then it moves on. So now people are doing a lot of work on natural language, trying to have the computer understand English sentences, what you mean, being able to answer some questions, and so on. So these are applications, but they have a huge economic impact, and even more in the future. So that has attracted a lot of attention from other scientists, from the media, and then from, of course, business people who are investing billions of dollars in this right now.
Yeah, is it exciting for you to be in the middle of this new development?
It is very exciting, and it's not something I had really expected, because 10 years ago when we started working on this, there were very few people in the world, maybe a handful of people interested in these questions. And initially it started very slowly. It was difficult to get money for these kinds of things. It was difficult to convince students to work on these kinds of things.
Or maybe you can explain to me the 10 years or whatever,
yes.
12 years ago you were with 3 people, and then you because it was not popular.
Right, that's right, that's right.
Thing.
Yes, that's right. So there has been a decade before the last decade where this kind of research essentially went out of fashion. People moved on to other interests. They lost the ambition to actually get AI, to get machines to be as intelligent as us. And also the connection between neuroscience and machine learning, it got a bit divorced. But a few people, including myself and Jeff Hinton and Yann LeCun, continued doing this, and we started to have good results. And other people, in the world were also doing this, and more people joined us. And in a matter of about 5 years, it started to be a more accepted area. And then the applications, the success in applications started to happen. And now it's crazy. I mean, we get hundreds of applicants, for example, for doing grad studies here, and companies are hiring like crazy and buying scientists for their research labs.
Really? You noticed that? Do they approach you as well?
Yeah.
The big companies?
Yes. So I could be much richer, but I chose to stay in academia.
But so you've made some right, did some good thinking, and now it has become popular.
Yes.
But it has become valuable as well.
Yes, very valuable. Yes.
Why? Maybe.
Basically, it's at the heart of what companies like Google, Microsoft, IBM, Facebook, Samsung, Amazon, Twitter,
Why is
all
this?
of these companies, they see this as a key technology for their future products and some of the existing products already.
And are they right?
Yeah, they are. Of course, I don't have a crystal ball, so there are a lot of research questions which remain unsolved, and it might take just a couple of years or decades to solve them. We don't know. But even if, say, scientific research on topics stopped right now, and you took the current state of the art in terms of the science, and you just applied it, right? Collecting lots of data sets and because these algorithms need a lot of data. Just applying the current science would already have a huge impact on society. So they're not. I don't think they're making a very risky bet. But it could be even better because we could actually approach human level intelligence.
You know that, or you think so?
We could. I think that we'll have other challenges to deal with. And some of them we currently know are in front of us. Others we probably will discover when we get there.
So now you're in the middle of a field of exciting research.
Yeah.
Because you know you're right, and you have a goal, and sometimes you see it clearly, and it has become popular. A lot of people want to study here, and and a lot of companies want to invest in you. So you must feel a lot of attention or a lot of
it's true.
attraction.
It's true.
How does it feel to be in the middle of this development?
So initially, it's exhilarating to have all this attention, and it's great to have all this recognition, and also it's great to attract really the best minds that are coming here for doing PhDs and things like that. It's absolutely great. But sometimes I feel that it's a bit too much, that I don't deserve that much attention, and that all these interactions with media and so on are taking time away from my research. And so it's, I have to find the right balance here. I think it is really important to continue to explain what we're doing so that more people can learn about it and take advantage of it or become researchers themselves in this area. But I need to also focus on my main strength, which is not speaking to journalists. My main strength is to come up with new ideas, crazy schemes, and interacting with students to build new things.
Have you thought of the possibility that you're wrong?
Well, of course, science is an exploration, and I'm often wrong. I propose 10 things, 9 of which end up not working, but we make progress. So I get frequent positive feedback that tells me that we're moving in the right direction.
you're right enough to go
Yes,
on.
yes. Yeah. And these days, because the number of people working on this has grown really fast, the rate at which advances come is incredible, right? The speed of progress in this field has greatly accelerated, and mostly because there are more people doing it.
And this is also reflected in what the companies do with it?
Yes, so companies are investing a lot in basic research in this field, which is unusual, right? Typically, companies would invest in applied research, where they take existing algorithms and try to use them for products. But right now, there's a big war between these big IT companies to attract talent, and also they understand that there's the potential impact, the potential benefit of future research is probably even greater than what we have already achieved. So for these two reasons, they have invested a lot in basic research, and they are basically making offers to professors and students in the field to come work with them in an environment that looks a little bit like what you have in universities, where they have a lot of freedom, they can publish, they can go to conferences and talk to their peers. So it's a good time for the progress of science, because companies are working in the same direction as universities towards really fundamental questions.
But then they own it. That's the difference.
So, yeah, that's something that's one of the reasons why I'm staying in academia. I want to make sure that what I do is going to be not owned by a particular person, but available for anyone.
But is that the risk? Is that really a risk, that because the knowledge is owned by a company, why would that be a risk? Maybe
I don't think it's a big deal right now. So the major industrial research centers, they publish a lot of what they do, and they have they do have patents, but they say that these patents are protective. So in case somebody would sue them, but they won't prevent other companies from using their technology. At least that's what they say. So right now, there is a lot of openness in the business environment for this field. We'll see how things are in the future. There's always a danger of companies coming to a point where they become protective, but then what I think is that companies who pull themselves out of the community and not participate to the scientific progress and exchange with the others, they will not progress as fast. And I think that's the reason why they're doing this. They understand that if they want to receive the most benefits from this progress, they have to be part of the public game of exchanging information and not keeping information secret.
Part of the mind of the universe.
Yes, exactly. Part of the collective that we're building of all our ideas and our understanding of the world. And there is something about doing it, participating into it, that enables us to be more powerful in this understanding. If we're just trying to be consumers of ideas, we're not mastering those ideas as well as if we're actually trying to improve them. So when we do research, we get on top of things much more than if we're simply trying to understand some existing paper and trying to use it for some product. So there's something that is strongly enabling for companies to do that kind of stuff. But that's new. It's 1 decade ago, for example, many companies were shutting down their research labs and so on. So it was a different spirit. But right now, the spirit is openness, sharing, and participating in a sort of common development of ideas through science and publication and so on.
It's funny that you say basic research, it's the same thing as fundamental research.
Yes.
That it becomes popular in some way.
Well, I think, first of all, it's appealing. I mean, as a person, if I'm a researcher, a PhD candidate, or a professor or something, it's much more appealing to me to know that what I do will be a contribution to humanity, right? Rather than something secret that only I and a few people will know about, and maybe some people will make a lot of money out of it, but I don't think it's as satisfying. And as I said, I think there are circumstances right now that even from purely an economic point of view, it's more interesting for companies to share right now and be part of the research.
So I think for us to understand what you're really into, I would like to know from you some basic definitions.
Yes.
For example, what in your way of thinking is, would you describe thinking?
Yes.
What is thinking?
Right. Well, obviously we don't know, because the brain is still...
What do we not know?
We don't know how the brain works. We have a lot of information about it. Too much, maybe, but not enough of the kind that allows us to figure out the basic principles of how we think and what does it mean at a very abstract level. But of course, I have my own understanding, so I can share that. And with the kinds of equations I drew on the board there, and other people in my field, there's this notion that what thinking is about is adjusting your mental configuration to be more coherent, more consistent with everything you've observed, right? And more typically the things you're thinking about or what you're currently observing. So if I observe a picture, my neurons change their state to be in agreement with that picture. And in agreement, given everything that the brain already knows, means that they are looking for an interpretation for that image, which may be related to things I could do that are related, like maybe, oh, I see this, I need to go there because it tells me a message that matters to me. So everything we know is somehow built in this internal model of the world that our brain has. And we get all these pieces of evidence each time we hear something, we listen to something, and our brain is accumulating all that stuff. And then what it does is try to make sense of it, reconcile the pieces like the pieces of a puzzle. And so sometimes, it happens to you, something clicks, right? Suddenly you see a connection that explains different things. Your brain does that all the time, not always that you get this conscious impression. And thinking is this, according to me. It's finding structure and meaning in the things that we are observing and that we've seen. And that's also what science does, right? Science is about finding explanations for what is around us. But thinking is happening in our head, whereas science is a social thing.
And it's outside your head.
Science has a part inside. Yeah, science has a part inside, of course, because we are thinking when we do science. But science has a social aspect. Science is a community of minds working together, and a history of minds having, discovered concepts that explain the world around us, and sharing that in ways that are efficient.
Just a second. Ik ben af en toe bang en kruip naar de camera. Nee, dat gaat helemaal goed. Dat ik in dit...
One thing I could talk about too is learning. Right? You told me asking about thinking, but I think a very important concept in my area is learning. I think I can explain how that can happen in those models or brains.
We'll get to that.
Yeah.
Ja, maar ik denk de hele tijd van, dat zie je op die camera.
Ja.
En dan is het
Deze?
opgelost. Ja.
Nee, dat ik jou zie.
Nee, als iemand binnenkomt.
Oh, hij zit nu precies achter hem zelfs. Nee, dat is helemaal goed. Het is alleen qua geluid even.
Ja.
Maar als je hem ziet zitten, is het niet erg.
Nee, daarom. Daarom is dat een handige camera. Ja, als er iets gebeurt buiten het kader, dan vliegt het op.
Gewoon doorgelopen, hè?
Ja. Okay, lopen nog?
Yeah.
So you explained what thinking is. now I would like to know what is intelligence?
That's a good question. I don't think that there's a consensus on that either.
On what?
On what is intelligence.
If you reframe my question, then I can...
Okay. So what is intelligence? That's a good question, and I don't think that there's a consensus, but in my area of research, people generally understand intelligence as the ability to take good decisions. And what good decisions? Like good for me, right?
Oh, okay.
Good in the sense that they allow me to achieve my goals, to, if I was an animal, to survive my predators, to find food, to find mates. And for humans, good might be achieving social status or being happy or whatever, it's hidden in your mind. What is it that's good for you? But somehow we are striving to take decisions that are good for us. And in order to do that, it's very clear that we need some form of knowledge. So even a mouse that's choosing to go left or right in a maze is using knowledge. And that kind of knowledge is not necessarily the kind of knowledge you find in a book, right? The mouse cannot read a book, cannot write a book, but in the mouse's brain, there is knowledge about how to control the mouse's body in order to survive, to find food, and so on. So the mouse is actually very intelligent in the context of the life of a mouse. If you were suddenly teleported in a mouse, you would probably find it difficult to do the right things. So intelligence is about taking right decision, and it requires knowledge. And now the question is, to build intelligent machines or to understand how humans and animals are intelligent, where are we getting the knowledge? Where can we get the knowledge? And some of it is hardwired in your brain from birth, right? And some of it is going to be learned through experience. And that's the thing that we're studying in my field. How do we learn, or rather, what are the mathematical principles for learning that could be applied to computers and not just trying to figure out how animals learn?
And there we get to the point, the learning.
Right.
So, can you explain to me, because for everybody else, you think of learning, you learn at school.
Yeah.
And you read books, and there's someone telling you how the world works. So, what in your concept is the definition of learning?
Yes, my definition of learning is not the kind of learning that people think about when they are in school and listening to a teacher. Learning is something we do all the time. Our brain is changing all the time in response to what we are seeing, experiencing. And it's an adaptation, and we're not just storing in our brain our experiences. It's not learning by heart. That's easy. A file in a computer is like learning by heart. You can store facts. But that's trivial. That's not what learning really is about. Learning is about integrating the information we're getting through experience into some more abstract form that allows us to take good decisions, that allow us to predict what will happen next, that allow us to understand the connections between things we've seen. So that's what learning is really about. In my field, we talk about the notion of generalization, so that the machine can generalize from things it has seen and learned from to new situations. That's the kind of learning we talk about in my field. And the way we typically do it in machines and how we think it's happening in the brain is that it's a slow, gradual process. Each time you live an experience, 1 second of your life, there's going to be some changes in your brain, small changes. So it's like your whole system is gradually shifting towards what would make it take better decisions. So that's how you get to be intelligent, right? Because you learn, meaning you change the way you perceive and act, so that next time you would see something, you would have some experience similar to what happened before, you would act better, or you would predict better what would have happened.
So it's very experience-based.
Yes, learning is completely experience-based. Of course, in school we think of learning as teaching knowledge from a book or some blackboard, but that's not really the main kind of learning. There is some learning happening when the student integrates all that information and tries to make sense of it. But just storing those facts is kind of useless.
Is the difference that you have to have an interest in it?
Well, motivation for humans is very important because we are wired like this. The reason we are wired like this is there are so many things happening around us that emotions help us to filter and focus on some aspects more than others, those that matter to us, right? And so motivation might be fear as well, sometimes. But for computers, basically they will learn what we ask them to learn. We don't need to introduce motivation or emotions. At least up to now, we haven't needed to do that.
But when you explained this deep learning,
yes,
to me,
yes.
Maybe from the perspective of a machine and a human, you can learn a computer experience, I think, but not interest. Or
well, you can. Emotions are something we're born with. We're born with circuits that make us experience emotions because some situations matter more to us. So in the case of the computer, we also, in a sense, hardwire these things by telling the computer, well, this matters more than that, and you have to learn to predict well here, and here it matters less. So we don't call that emotions, but it could play a similar role.
It looks like emotions.
Right.
But then it's still programmed.
Absolutely. So AI is completely programmed.
Yeah. But as I understand it well, you are searching in this area where this program, where it's beyond programming, that they start to think for themselves.
Okay, so there's an interesting connection between learning and programming. So the traditional way of putting knowledge into computers is to write a program that essentially contains all our knowledge, and step by step, where you tell the computer, if this happens, you do this, and then you do that, and then you do that, and then this happens, you do that, and so on and so on. That's what a program is. But when we allow the computer to learn, we also program it, but the program that is there is different. It's not a program that contains the knowledge we want a computer to have. We don't program the computer with the knowledge of doors and cars and images and sounds. We program the computer with the ability to learn. And then the computer experiences images or videos or sounds or texts, and learns the knowledge from those experiences. So you can think of the learning program as a meta program, and we have something like that in our brain. So if one part of your cortex dies, you have an accident. That part used to be doing some job, like maybe interpreting music or some types of songs or something. Well, if you continue listening to music, then some other part will take over. And that function may have been sort of impaired for some time, but then it will be taken on by some other part of your cortex. What does that mean? It means that the same program that does the learning was there in those two regions of your cortex, the one that used to be doing the job and the one that does it now. And that means that your brain has this general purpose learning recipe that it can apply to different problems, and that this different parts of your brain will be specialized on different tasks depending on what you do and how the brain is connected. If we remove that part of your brain, then some other parts will start doing the job, if the job is needed, because you do those experiences, right? So if I had a part of my brain that was essentially dealing with playing tennis, and that part dies, I'm not going to be able to play tennis anymore. But if I continue practicing, it's going to come back. And that means that the same learning, general purpose learning recipe is used everywhere, at least in cortex. And this is important not just for understanding brains, but for companies building products, because we have this general purpose recipe or family of recipes that can be applied for many tasks. The only thing that really differs between those different tasks is the data, the examples that the computer sees. So that's why companies are so excited about this, because they can use this for many problems that they want to solve, so long as they can teach the machine by showing it examples.
Is it always, is learning always positive?
Learning is positive by construction in the sense that it's moving the learner towards a state of understanding of its experiences. So in general, yes, because learning is about improving something. Now, if the something you're improving is not the thing you should be improving, then you could be in trouble. Like we could learn, people could be trained into a wrong understanding of the world, and then they start doing bad things, right? So that's why education is so important for humans. And for machines right now, the things we're asking the machines to do are very simple, like understanding the content of images and text and videos and things like that, right?
So learning is not per se positive, because also you can learn wrong things.
Right, but if you're just observing things around you, taken randomly, then it's just what the world is, right?
And that's a state of the some kind of primitive learning of computers right now, or?
Right now, yeah. The learning that computers do is very primitive. It's mostly about perception, and in the case of language, some kind of semantic understanding, but it's still a pretty low-level understanding.
Yeah. But is it possible for you to explain in a simple way how is it possible for a computer to learn?
So the way that the computer is learning is by small iterative changes, right? So let's go back to my artificial neural network, which is a bunch of neurons connected to each other, and they're connected through these synaptic connections. And at each of these connections, there is the strength of the connection, which controls how a neuron influences another neuron. So you can think of that strength as a knob. And what happens during learning is those knobs change. We don't know how they change in the brain, but in our algorithms, we know how they change, and we understand mathematically why it makes sense to do that. And they change a little bit each time you see an example. So I show the image of a cat, but the computer says it's a dog. So I'm going to change those knobs so that it's going to be more likely that the computer is going to say cat. Maybe the computer outputs a score for dog and a score for cat. And so what we want to do is decrease the score for dog and increase the score for cat, so that the computer eventually, after seeing many millions of images, starts seeing the right class more often and eventually gets it as well as humans.
But that still sounds like putting just enough data, or in the end less data, for a computer to recognize something. But how do you know that a computer is learning? How do you know that you're...
Well, you can test it on new images, right? So if the computer was only learning by heart, copying the examples that it has seen, it wouldn't be able to recognize a new image of, say, a new breed of dog, or a new angle, new lighting. At the level of pixels, those images could be very, very different. But if the computer really figured catness, at least from the point of view of images, it will be able to recognize new images of new cats, taken in new postures, and so on. And that's what we call generalization. So we do that all the time. We test the computer to see if it can generalize to new examples, new images, new sentences.
Can you show that to us? Not right now, but
yeah.
You can show that proof of learning computer?
Yeah. I'll try to show you some examples of that. Yeah.
Oh, great. So, is there something I'm missing right now for understanding deep learning?
Yes.
Okay, tell me.
I thought this was a statement, not a question. Well, but yes, of course, there are many things that you're missing. So there are many interesting questions in deep learning, but one of the interesting challenges has to do with the question of supervised learning versus unsupervised learning. Right now, the way we teach the machine to do things or to recognize things is we use what's called supervised learning, where we tell the computer exactly what it should do or what output it should have for a given input. So let's say I'm showing it the image of a cat again. I tell the computer, this is a cat. And I have to show it millions of such images. That's not the way humans learn to see and understand the world or even understand language. For the most part, we just make sense of what we observe without having a teacher that is sitting by us and telling us every second of our life, this is a cat, this is a dog.
Supervisor.
That's right. There's no supervisor. I mean, we do get some feedback, but it's pretty rare. And sometimes it's only implicit. So you do something and you get a reward, but you don't know exactly what it was you did that gave you that reward, or you get you talk to somebody, the person is unhappy, and you're not sure exactly what you did that was wrong, and the person is not going to tell you, general, what you should have done. So this is called reinforcement learning, when you get some feedback, but it's a very weak, you did well or you didn't do well. Like you have an exam and you achieved 65%. Well, you don't know, if you don't know what the errors were and what the right answers are, it's very difficult to learn from that. But we are able to learn from that, from very weak signals or no reinforcement at all, no feedback, just by observation and trying to make sense of all of these pieces of information. That's called unsupervised learning. And we're not yet, we're much more advanced with supervised learning than with unsupervised learning. So all of the products that these companies are building right now, it's mostly based on supervised learning.
So the next step is unsupervised learning?
Yes.
Does it mean that unsupervised learning, that a computer can think for themselves?
That means the computer will be more autonomous in some sense, right? That don't need...
That's a hard one.
More autonomous, right?
Computer.
Well, more autonomous in its learning. We're not talking about robots here, right? We're just talking about computers gradually making sense of the world around us by observation. And we probably will still need to give them some guidance, but the question is how much guidance. Right now we have to give them a lot of guidance. Basically, we have to spell everything very precisely for them. So we're trying to move away from that so that they can essentially become more intelligent, because they can take advantage of all of the information out there, which doesn't come with a human that explains every bits and pieces.
But when a computer starts to learn,
yes,
is it possible to stop the computer from learning?
Sure.
How? It sounds like if it starts to learn, then it learns.
It's just a program running. It's stored in files. There's nothing there's no robot. There's no, at least in the work we do, it's just a program that contains files that are contains those synaptic weights, for example. As we see more examples, we change those files so that they will correspond to taking the right decisions. But there's no, those computers don't have a consciousness. There's no such thing, right now, at least, and for a while.
Is it right when I say, well, a deep learning or a self-learning computer, becoming more autonomous.
Autonomous in its learning, right?
Yes.
Yes.
Free.
Well, again, it's probably going to be a gradual thing where the computer requires less and less of our guidance. But we probably, so if you think about humans, we still need guidance. If you take a human and a baby, nobody wants to do that experiment, but you could imagine a baby being isolated from society. That child probably would not grow to be very intelligent, would not understand the world around us as well as we do. That's because we've had parents, teachers, and so on guide us, and we've been immersed in culture. So all that matters, and it's possible that it will also be required for computers to reach our level of intelligence. The same kind of attention we're giving to humans, we might need to give to computers. But right now, the amount of attention we have to give to computers for them to learn about very simple things is much larger than what we need to give to humans. Humans are much more autonomous in their learning than machines are right now. So we have a lot of progress to do in that direction.
Is the difference also just a simple fact that we have biology? Or?
Well, biology is not magical. Biology can be understood. It's what biologists are trying to do, and we understand a lot. But as far as the brain is concerned, there are still big holes in our understanding.
But so, I mean, a baby grows.
Yes.
But a computer doesn't.
Sure, it can. I mean, we can give it more memory and so on, right? So that you can grow the size of the model. That's not a big obstacle. I mean, computing power is an obstacle, but I'm pretty confident that over the next few years, we're going to see more and more computing power available, as it has been in the past, that will make it more possible to train models to do more complex tasks. Right.
So how do you tackle all the people who think this is a horror scenario? Because people start to think that robots, computers, and it's not about that.
So I think
you have to have a standpoint.
That's right. I do. So first of all, I think there's been a bit of excessive expression of fear about AI. Maybe because the progress has been so fast, it has made some people worried. But if you ask people like me who are into it every day, they're not worried because they can see how stupid the machines are right now and how much guidance they need to move forward. So to us, it looks like we're very far from human level intelligence and even, have no idea whether one day computers will be smarter than us. Now, that may be a short-term view. What will happen in the future is hard to say, but we can think about it, and I think it's good that some people are thinking about the potential dangers. I think it's difficult right now to have a grasp on what could go wrong, but with the kind of intelligence that we're building in machines right now, I'm not very worried. It's not the kind of intelligence that I could foresee exploding, becoming more and more intelligent by itself. I don't think that's plausible for the kinds of deep learning methods and so on. Even if they were much more powerful and so on, it's not something I can envision. That being said, it's good that there are people who are thinking about these long-term issues. One thing I'm more worried about is the use of technology now or in the next couple of years or 5 or 10 years, where the technology could be developed and used in a way that could either be very good for many people or not so good for many people. So, for example, military use and other uses which I think I would consider not appropriate are things we need to worry about.
Can you name examples of that?
Yeah. So there's been a fuss and a letter signed by a number of scientists who try to tell the world we should have a ban on the use of AI for autonomous weapons that could essentially take the decision to kill by themselves. So that's something that's not very far-fetched in terms of technology and the given science. Basically, the science is there, it's a matter of building these things. But it's not something we would like to see, and there could be an arms race of these things. So we need to prevent it. The same way that collectively the nations decided to have bans on biological weapons and chemical weapons, and to some extent on nuclear weapons. The same thing should be done for that. And then there are other uses of this technology, especially as it matures, which I think are questionable from an ethical point of view. So I think that the use of these technologies to convince you to do things, like with publicity and trying to influence, maybe think about influencing your vote, right? As the technology becomes really stronger, you could imagine people essentially using this technology to manipulate you in ways you don't realize, but is good for them, but it's not good for you. And I think we have to start being aware of that, and all the issues of privacy are connected to that as well. But in general, because we're training, currently companies are using these systems for advertisements where they're trying to predict what they should show you so that you will be more likely to buy some product, right? So it seems, not so bad, but if you push it, they might bring you into doing things that are not so good for you. I don't know, like smoking or whatever, right?
Well, we just stopped at a point where I was going to ask you about, is that why you wrote the manifest about diversity in thinking? Because
sorry, Kees.
if you, dit is toch allemaal nog maar een inleiding.
Oké. Gaan we door.
Because computers, you can learn them a lot of things, but it's almost unimaginable that you learn them diversity. Am I correct that has a connection? Or?
If you want, I will elaborate now. So you're asking me about diversity. And I can say several things. First of all, people who are not aware of the kinds of things we do in AI with machine learning, deep learning, and so on, may not realize that the algorithms, the methods we're using already include a lot of what may look like diversity, creativity. So for the same input, the computer could produce different answers. And so there's a bit of randomness, just like for us. Placed twice in the same situation, we don't always take the same decision. And there are good reasons for that, both for us and for computers. So that's the first part of it. But there's another aspect of diversity which I have studied in a paper a few years ago, which is maybe even more interesting. Diversity is very important, for example, for evolution to succeed, because evolution performs a kind of search in the space of genomes, of the blueprint of each individual's. And up to now, machine learning has considered what happens in a single individual, how we learn, how our machine can learn, but has not really investigated much the role of having a group of individuals learning together, so a kind of society. And in this paper a few years ago, I postulated that learning in an individual could get stuck. That if we were alone learning by observing the world around us, we might get stuck with poor models of the world. And we get unstuck by talking to other people and by learning from other people in the sense of they can communicate some of the ideas they have, how they interpret the world. And that's what culture is about. culture has many meanings, but that's the meaning that I have, that it's not just the accumulation of knowledge, but how knowledge gets created through communication and sharing. And what I postulated in that paper is that there is what's called an optimization problem that can get the learning of an individual to not progress anymore, in the sense that, as I said before, learning is a lot of small changes, but sometimes there's no small change that really makes you progress. So you need some kind of external kick that brings a new light to things. And another connection to evolution, the connection to evolution actually is that this small kick we get from others is like we are building on top of existing solutions that others have come up with. And of course, the process of science is very much like this. We're building on other scientists' ideas, but it's true for culture in general. And this actually makes the whole process of building more intelligent beings much more efficient. In fact, we know that since humans have made progress thanks to evolution and not just thanks to culture and not just to evolution, we've been making, our intelligence has been increasing much faster. So evolution is slow, whereas you can think of culture, the evolution of culture, as a process that's much more efficient because we are manipulating the right objects. So what does this mean in practice? It means that just like evolution needs diversity to succeed, because there are many different variants of the same type of genes that are randomly chosen and tried, and the best ones combined together to create new solutions. Just like this in cultural evolution, which is really important for our intelligence, as I was saying, we need diversity. We need not just one school of thought. We need to allow all kinds of exploration, most of which may fail. So in science, we need to be open to new ideas. Even it's very likely it's not going to work, it's good that people explore. Right? Otherwise, we're going to get stuck in the space of possible interpretations of the world, and it may take forever before we escape.
Is it like doing basic research that you don't have a specific goal?
That's right. So basic research is exploratory. It's not trying to build a product. It's just trying to understand, and it's going in all possible directions according to our intuitions of what may be more interesting, but without a strong constraint. So yeah, basic research is like this, but there's a danger because humans they like fashionable things and trends and compare each other and so on, that we're not giving enough freedom for exploration. And it's not just science, it's in general, right? In society, we should allow a lot more freedom. We should allow marginal ways of being and doing things to coexist.
But if you allow this freedom, of course, a lot of people think, well, don't go that way, because then you have autonomous, self-thinking computers creating their own diversity. And so there are a lot of scenarios which people think of because they don't know, which scare them. So
well, it's a gamble, and I'm more on the positive side. I think that the rewards we can get by having more intelligence in our machines is immense. And the way I think about it is, it's not a competition between machines and humans. Technology is expanding what we are. Thanks to technology, we are now already much stronger and more intelligent than we were. The same way that the Industrial Revolution has kind of increased our strength and our ability to do things physically, the sort of computer revolution and now the AI revolution is going to continue to increase our cognitive abilities.
It sounds very logical, but I can imagine you must get tired of all those people who don't will fear this development.
Right, but I think we should be conscious that a lot of that fear is due to a projection into things we are familiar with. So we are thinking of AI like we see them in movies. We're thinking of AI like we see some kind of alien from another planet, like we see animals. When we think about another being, we think that other being is like us. And so we are greedy. We want to dominate the rest. And if our survival is at stake, we're ready to kill, right? So we project that some machine is going to be just like us. And if that machine is more powerful than we are, then we're in deep trouble, right? So it's just because we are making that projection. But actually, the machines are not some being that has an ego and a survival instinct. It's actually something we decide to put together. It's a program. And so we should be smart enough and wise enough to program these machines to be useful to us rather than go towards their own needs. They will cater to our needs because we will design them that way.
I understand that, but then there's also this theory of, suppose you can develop machines or robots that can self-learn.
Mm-hmm.
So if that grows with this power of
yes,
there is some acceleration in their intelligence, or that's
maybe not. I don't. That's not the way what you're saying is appealing if I was to read a science fiction book, but it doesn't correspond to how I see AI and the kinds of AI we're doing. I don't see such acceleration. In fact, what I see is the opposite. What I foresee is more like barriers than acceleration. So
slowing it down.
Yes. So our experience in research is that we make progress, and then we encounter a barrier, a difficult challenge, a difficulty. The algorithm goes so far, and then it can't make progress. Even if we have more compute power, that's not really the issue. The issue are like basically computer science issues, that things get harder as you try to solve, exponentially harder, really much harder as you try to solve more complex problems. So it's actually the opposite, I think, that happens. And I think that would also explain maybe to some extent why we're not super intelligent ourselves. I mean, the sense that our intelligence is kind of limited. There are many things for which we take the wrong decision, and it's true also of animals. Like, why is it that some animals have much larger brains than we do, and they're not that smart? And you could come up with a bunch of reasons, but it's not. They have a bigger brain, right? So, and their brain, like a mammal's brain, is very, very close to ours. So it's hard to say. Now, I think it's fair to consider the worst scenarios and to study it and have people really seriously considering what could happen and how we could prevent any dangerous thing. I think it's actually important that some people do that. But right now, I see this as a very long-term potential, and the most plausible scenario is not that, according to my vision.
Does it have to do with the fact that you try to develop this deep learning? That if you know how it works, then you also know how to deal with it. Is that why you are confident in not seeing any problem?
You're right. That I think we are more afraid of things we don't understand, and scientists who are working with deep learning every day don't feel that they have anything to fear because they understand what's going on, and they can see clearly that there is no danger that's foreseeable. So you're right, that's part of it. There's the psychology of seeing the machine as some other being. There's the lack of knowledge. There is the influence of science fiction. So all of these factors come together, and also the fact that the technology has been making a lot of progress recently. So all of that, I think, creates a kind of exaggerated fear. I'm not saying we shouldn't have any fear. I'm just saying it's exaggerated right now.
is your main part of life, or how you fill the day. Is that thinking? Is your work thinking? What do you physically do?
I'm thinking all the time, yes. And whether I'm thinking on the things that matter to me the most, maybe not enough. Managing a big institute with a lot of students and so on means my time is dispersed. But when I can, focus, or when I'm in a scientific discussion with people and so on, of course, there's a lot of thinking, and it's really important. That's how we move forward.
Yeah, what does it mean? But the first question I asked you was about what is thinking.
Yes.
And now we are back to that question.
Yeah. So
you are a thinker. So what happens?
Okay.
During the day?
Yes.
With you.
So when I listen to somebody explaining something, maybe one of my students talking about an experiment, or another researcher talking about their idea, something builds up in my mind to try to understand what is going on, and that's already thinking. But then things happen, so other pieces of information and understanding connect to this, and I see some flaw or some connection, and that's where the creativity comes in, and I have the impulse of talking about it, and that's just one turn in a discussion, and we go like this, and new ideas spring like this, and it's very, very rewarding.
Is it possible for you not to think?
Well, yes, it is possible not to think. It's hard, but if you really, relax, or you are experiencing something very intensely, then you're not into your thoughts. You're into just some present time experience. Yes.
Like it's more emotional rather than rational?
For example, yes. But thinking isn't just rational. A lot of it is, I don't mean it's irrational, but a lot of the thinking is something that happens somehow behind the scenes. It has to do with intuition, that has to do with analogies. And it's not necessarily A causes B causes C. It's not that kind of logical thinking that's going on in my mind most of the time. It's much softer, and that's why we need the math in order to filter and fine-tune the ideas. But the raw thinking is very fuzzy, and but it's very rich because it's connecting a lot of things together, and it's discovering the inconsistencies that allow us to move to the next stage and solve problems.
Are you aware of that you are in that situation when you are thinking?
It happens to me. I used to spend some time meditating, and there you learn to pay attention to your own thoughts. So it does happen to me. It happens to me also that I get so immersed in my thoughts in ordinary daily activities that people think that I'm very distracted and not present, and they can be offended. But it's not always like this. Sometimes I'm actually very, very present. I can be very, very present to somebody talking to me. And that's really important for my job, right? Because if I listen to somebody in a way that's not complete, I can't really understand fully and participate in a rich exchange.
I can imagine that when you are focused on a thought,
yeah.
you are having this problem and you're thinking about it, about it. And then you are in a situation that other people demand something else of you.
Right.
Like attention from your children or whatever.
Yes.
Then there's something in you which decides to keep on focused, or how does it work with you?
Right.
You don't want to lose the thought, of course.
That's right. So I have some notebooks, I write my ideas. Often when I wake up, or sometimes an idea comes and I want to write it down, like if I was afraid of losing it. But actually the good ideas, they don't go away. It turns out very often I write them, but I don't even go back to reading them. It's just that it makes me feel better and it anchors. Also the fact of writing an idea kind of makes it take more room in my mind. And there's also something to be said about concentration. So my work now, because I'm immersed with so many people, can be very distractive. But to really make big progress in science, I also need times when I can be very focused and where the ideas about a problem and the different points of view and all the elements sort of fill my mind. I'm completely filled with this. That's when you can be really productive. And it might take a long time before you reach that state. Sometimes it could take years for a student to really go deep into a subject so that he can be fully immersed in it. And that's when you can really start seeing through things and getting things to stand together and solidly. And now you can extend science, right? Now when things are solid in your mind, you can move forward.
Like a phase of understanding.
Yeah. When you need enough concentration on something to really get these moves. There's the other mode of thinking, which is the brainstorming mode, where out of the blue I start a discussion. 5 minutes later, something comes up. So that's more like random, and it's also very. It could be very productive as well. It depends on the stimulation from someone else. So someone introduces a problem, and immediately I get something comes up, and we have maybe an exchange. So that's more superficial, but a lot of good things come out of that exchange because of the brainstorming. Whereas there's the other mode of thinking, which is I'm alone, nobody bothers me, nobody's asking for my attention, I'm walking, I'm half asleep, and there I can fully concentrate, eyes closed, or not really paying attention to what's going on in front of me because I'm completely in my thoughts.
When do you think?
When?
Yeah. During the day. Let's start a day.
So the time when the two times when I spend more on this concentrated thinking is usually when I wake up and when I'm walking back and forth between home and university.
Just enlarge this moment. And what happens?
Well, so I emerge to consciousness, like everybody does every morning, and eyes closed and so on, and some thought related to a research question or maybe non-research question comes up, and if I'm interested in it, I start like going deeper into it, and
still your eyes closed?
Still my eyes closed, and then it's like if you see a thread dangling and you pull on it, and then more stuff comes down, and now you see more things and you pull more, and like there's an avalanche of things coming, right? So the more you pull on those strings, and the more new things come or information comes together. And sometimes it goes nowhere, and sometimes that's how new ideas come about.
And at what stage in this pulling the thread you open your eyes?
I could stay like this for an hour.
Eyes closed.
Yeah.
Pulling the thread.
Yes.
Seeing what's happening.
Yeah. Often what happens is I see something that I haven't seen before and I get too excited, so that wakes me up and I want to write it down. So I have my notebook not far and I write it down. Or I want to send an email to somebody saying, oh, I thought about this, and it's like 6 a.m. and and they wonder if I'm working all the time.
Yeah. So, and then what happens then? Then you woke up? Or you open your eyes, or you wrote it down?
Well, so once I'm writing it down, my eyes are open, and it's like I feel relieved, right? It's like, okay, now I can go and maybe have breakfast or take a shower or something. So having written it down, and it might take some time to write it down. Also, sometimes I write an email and then it's longer. And now the act of writing it is a different thing. So there's the initial sort of spark of vision, which is still very fuzzy. But then when you have to communicate the idea to someone else, say in an email, you have to really make a different kind of effort. You realize some flaws in your initial ideas and you have to clean it up and make sure it's understandable. And now it takes a different form. And sometimes you realize when you do it that it was nothing really. Yeah, it was just half dream. Yeah.
And what does your partner think of? There he is again with some idea.
I didn't understand the question.
But and what does your partner think of this? That you wake up and then you have to write something down.
She's fine with that. I think she's glad to see this kind of thing happen. She's happy for me that I live these very rewarding moments.
But she understands what happens.
Yeah. I mean, I tell her often, I just had an idea.
Yeah.
I want to say, I just want to.
Does she understand?
What do you mean, the science?
Yes.
No. But she understands that it's really important for me, and this is how I move forward in my work, and also how emotionally fulfilling it is.
Okay, and then you at a sudden moment of you have to go to work.
Yes.
Let's talk about the walk you do every day.
Yes.
So what does it mean?
So that walk is, you can really think of it as a kind of meditation. So
tell me
you
about
walk.
What you're doing, if you want to. So every day I walk for half an hour.
Yeah. So every day I walk up the hill from my home to the university, and it's about half an hour, and it's more or less always the same path. And because I know this path so well, I don't have to really pay much attention to what's going on, and I can just relax and let thoughts go by and eventually focus on something, or not. Sometimes it's just maybe more in the evening where I'm tired, maybe just a way to relax and let go.
Like a quality thinking time?
Yes, absolutely. Because I'm not bombarded by the outside world. I can just.
Normal people are bombarded by every signs and cars and sounds.
Yeah, but
and with the weather.
Yeah, I kind of ignore that.
So you are. When there are thoughts around you.
So, when I was young, I used to hit my head on on poles.
Because you were thinking.
Yeah, or reading while walking.
So, and now it doesn't happen anymore.
No. Well, actually it does now, because I sometimes check my phone. I see lots of people do that, not paying attention to what's going on. Yeah.
So, well, we will film your walk. Maybe something happens. But are there, during this walk, if you do it for such a long time, walking uphill, That's kind of a nice metaphor, walking up the hill.
Yeah.
Are there on this route situations or positions or places where you had some really good ideas that you can remember? Well, I was waiting at the traffic light, or that was this.
Yeah, I have some memories of specific moments going up, thinking about some of the ideas that I have been going through my mind over the last year in particular. I guess these are more recent memories. So
can you enlarge one of those moments like you did with waking up?
Right. So, as I said earlier, it's like if the rest of the world is in a haze, right? It's like there's automatic control of the walking and watching for other people and cars potentially. But it's like if I had a 3D projection of my thoughts in front of me that are taking most of the room, and my thinking works a lot by visualization, and I think a lot of people are like this. It's a very nice tool that we have, using our kind of visual analogies to understand things, even if it's not a faithful portrait of what's going on. The visual analogies are really helping me, at least, to make sense of things. So it's like if I had pictures in my mind to illustrate what's going on. And it's like I see little, what do I see? I see information flow in neural networks. It's like if I was running a simulation in my mind of what would happen if some rule of conduct was followed by in this algorithm, in this process.
And that's when you walk up the hill, that's what you see.
Yeah. So it's like if I was running a computer simulation in my mind to try to figure out what would happen if I made such choices, or if we consider such equation, and what would it entail, what would happen, imagine different situations, and then and of course it's not as detailed as if we did a real computer simulation, but it provides a lot of insight for what's going on.
But then you walk up the hill every day, and describe the most defining moment during one of those walks. Where you were, where you stood, which corner, or what?
Well, so I remember a particular moment. I was walking on the north sidewalk of the Queen Mary Street, and I was seeing the big church we have there, which is called the Oratoire. It's beautiful. And then I got this insight about perturbations propagating in brains.
Maybe you want to do that
again. From the beginning, or just the last sentence?
The last one.
And so then I got this insight as visually of these perturbations happening on neurons that propagate to other neurons and propagate to other neurons. And it was like I'm doing with my hands, but it was like something visual. And suddenly I had the thought that this could work, that this could explain things that I was trying to understand.
How did this feel?
Great. I think of all the good feelings that we can have in life, the feeling we get when something clicks, the eureka, is probably maybe the strongest, the most powerful, the one that we can seek again and again, and only brings positive things. maybe stronger than food and sex and those usual good things we get from our experience.
You mean this moment?
These kinds of moments provide pleasure. It's a different kind of pleasure, just like different pleasures, a different sensory pleasure, and so on. But it's really like, I think when your brain realizes something, understands something, it's like you send yourself some molecules to reward you. Say, oh, great, do it again if you can, right?
And did you do it again?
Yeah, that's my job.
So this is one moment at the church. Was it a coincidence that it was at a church?
No.
There's nothing to do with it.
I don't believe in God.
But I don't believe in God either. But if you think of God as someone who created us as his, and he is our example.
Yes.
Trying to understand what's happening in your head or your brain.
Yes.
Isn't that what other people call God? Or looking for?
I'm not sure I understand your question.
How can I rephrase that one? When you understand how a brain works,
yes,
maybe then you understand who God is.
When we understand how brains work, we understand who we are to some extent. I mean, a very important part of us. That's one of my motivations. And the process of doing it is something that defines us individually, but also as a collective, as a group, as a society. So there may be some connections to religion which are about connecting us to some extent.
Yeah, it's one of those layers that you were talking about. That a religion is one of them, of course.
Yep.
So, but during this, it's half an hour, then you are almost here. So.
Sometimes I think it's too short, but then I have things to do. So. Yeah.
But let's continue this metaphor. It's uphill. When you are uphill, what do you see?
I feel, so when I'm going uphill, my body's working hard. I mean, I'm not running, but I'm walking and I can feel the muscles warming up and my whole body becoming more full with energy. And I think that helps the brain as well. That's how it feels anyway.
But I mean, when Moses went up to the mountain,
right.
And then he saw the promised land. When you go uphill,
yes.
What do you see?
When I go uphill, I see the university, but there's something that's related to your question, which is each time I have these insights, these eureka moments, it's like seeing the promised land. It's very much like that. It's like you have a glimpse of something you had never seen before, and it looks great. And you feel like you now see a path to go there. So I think it's very, very close to this idea of seeing the promised land. But of course, it's not just one promised land. It's one step to the next valley and the next valley, and that's how we climb really big mountains.
So, is there anything you want to add to this yourself? Because I think we are ready now to go uphill.
Yeah, fine.
Maybe just a few questions about Friday. So, what you're going to do? What are you going to do on Friday?
So Friday, I'm going to make a presentation to the rest of the researchers in the lab, in the institute, about one of the topics I'm most excited about these days, which is trying to bridge the gap between what we do in machine learning, which has to do with AI and building intelligent machines, and the brain. I'm not really a brain expert, I'm more a machine learning person, but I talk to neuroscientists and so on, and I really care about the big question of how is the brain doing the really complex things that it does. And so the work I'm going to tell about Friday is one of small step in that direction that we've achieved in the last few months.
On your path to the promised land.
Yes, exactly. That's right. And I've been making those small steps, on this particular topic for about a year and a half. So it's not like just something happens and you're there, right? It's a lot of insights that make you move and get understanding, and science makes progress by steps. Most of those steps are small, some are slightly bigger. Seen from the outside, sometimes people have the impression that, there's this big breakthrough, and journalists like to talk about breakthrough. But actually, science is very, very progressive because we gradually understand better the world.